All right, this video is just a review over the last section in Chapter 8, specifically about intermolecular forces. Okay, so there is a difference inter versus intra. Intra is what we started talking about in Chapter 7 and Chapter 8. Intra means within. So those are all of the bonds and forces that are within the molecule themselves. So what that means, aka that would be the ionic bonds and the covalent bonds. So those are within the molecules. Then for the intermolecular forces, the inter, even though it sounds like it's intra means within, inter means outside. So intermolecular forces are outside the molecules. All right, and we have three intermolecular forces that we need to know. One is called London dispersion force, or LDF. Then we have dipole interactions. And last but not least, we have hydrogen bonding. Now, there are more, and if you will take AP chemistry, you will learn more intermolecular forces, but those are the three main ones that we need to know in Chemistry 1. So, intermolecular forces are weaker than intramolecular forces. It's a lot harder to break up ionic and covalent bonds than it would be to break up anything outside the molecule. Okay? And in increasing order from weakest to strongest, the weakest of all of these that are listed are LDFs, London dispersion force, then dipole interaction, then hydrogen bonding. So those are the order of the intermolecular forces. And then next we can continue ordering with our intra would be covalent bonds. And last but not least, the most strongest out of everything here are ionic bonds. So knowing that the order from weakest to strongest is important, in addition to being able to understand the difference between outside the molecule versus within the molecule. All right, so let's talk about what those intermolecular forces are. We're going to start with dispersion, the weakest of all of them. So talking here about the LDF, also known as dispersion. Now, dispersion happens with all intermolecular force examples. Because it happens within both polar molecules and nonpolar. So when it's with polar molecules, it's very easy to see, and it just helps make the other intermolecular forces stronger. The nonpolar is what we're going to focus on because that is the one that's difficult to understand. Okay, so this is specifically nonpolar LDF. Well, the reason why I'm talking about nonpolar, when you look at the original molecule, it's nonpolar. Okay, so notice here how we have 3 unshared pairs on the left bromine and 3 unshared pairs on the right bromine. So this is the structure of BR2. Okay, well, what happens in order to create London dispersion forces, in order for this bromine gas molecule or bromine liquid molecule to interact with other things, is we have what's called an instantaneous dipole. Oops, spelled that wrong. I don't like how that red looks. Instantaneous dipole. And what the instantaneous dipole means is it has the electrons move in the molecule, okay? So instead of being nice and symmetrical, like the Br2 should be when it's nonpolar, it has a shift in those electrons. The electrons move around. So when the electrons move around, notice how, and this is just an estimation of what happens. I don't know if it really happens or not, but what I did was, if there's a total of 6 unshared pairs, I moved so that there was 5 on one side and only 1 left on the other side. And so with creating this instantaneous dipole by having the electrons move, now we have a slightly negative side and a slightly positive side. So when you have that slight charge, that instantaneous dipole, that allows it to then interact with other molecules. So like it could interact, oops, that's a nonpolar, just kidding. It could interact with another Br2 molecule that has been moved, the electrons have been moved around, where it would create like a bond here. That would be our LDF area. Or it could react with like a polar molecule. So HF is polar, right? So we could have an LDF interaction form there because on this molecule, the hydrogen would be the slightly positive part, and then the fluorine would be the slightly negative. Okay, so this instantaneous dipole happens with the electrons moving, so then we can have the interactions take place. The reason why London dispersion force is so weak is because of this instantaneous dipole. It doesn't want to be like this. It wants to be back in its original nonpolar symmetrical self. So something will have to happen, and it depends. Is it stronger to be nonpolar, or is it stronger to be bonded with something else or held together by a different force? And so usually going back to its nonpolar self is the better way, what it likes to do, and so that's why LDF is weakest in nonpolar structures. Okay, next is dipole interactions. I usually just call them dipole. You can call them dipole. Dipole interactions, dipole interactions. Dipole interactions happen with polar molecules. So there's no instantaneous dipole because the molecules are already polar. All right? And remember, when you see that, you're going to see just a molecule that's already polar, like this. This is OF2, oxygen difluoride. Okay, and here there's electrons everywhere, but oxygen has less electrons than the fluorine does. So the fluorines would be the slightly negatives and the oxygen would be the slightly positive. Okay, and so since it's already polar, that tells us that it would be dipole interaction in addition to LDF. Okay, so if we had 2 OF2 molecules, the interaction would happen between the oxygen of one, the slightly positive side, with the slightly negative of a different molecule. So this right here would create an interaction, and that interaction would be your dipole-dipole, or dipole interaction. Okay? And remember too, it's also London dispersion force, because everything has London dispersion force helping it to stay together. And the dipole interactions, they can interact like if we had this NH3 molecule, the nitrogen is the slightly negative side. So you could have an interaction here between the nitrogen and the oxygen, which is kind of weird that I have to turn it like that, but that could happen. So you can have lots of different molecules, or you can have the same molecule all being held together by these intermolecular attractions. Okay, and then the last type of intermolecular attraction is hydrogen bonding. Or I sometimes just write H bond for short. Now, hydrogen bonding happens with polar molecules, but it specifically has hydrogen paired up, bonded with electronegative atoms like fluorine, oxygen, nitrogen, and chlorine. Okay, so if you see hydrogen involved, it's probably going to be hydrogen bonding, but you also look for a fluorine, a chlorine ion, or a nitrogen or an oxygen as well. Okay, so this NH3, this could have hydrogen bonding because it has, within one molecule, it has hydrogen with the nitrogen bonded. So we could have a hydrogen bond created right there between the nitrogen of one and the hydrogen of the other. Okay. Another example, a very common example, is our universal solvent, which is water, a big H2O. Okay. And so on water, the hydrogens are slightly positive, oxygens are slightly negative. So the interaction would be between the water, the H from one, and the oxygen from the other. Okay, so that would be your H bond. And LDF. So sometimes when you look at the pictures that I've drawn in the past, there might be like the squiggle lines, there might be dotted lines. The full lines are those intramolecular forces. Like, I don't want to write on my paper, but this right here would be the intramolecular, and this is intermolecular, because intra is within one molecule by itself, and inter is within the two, outside the molecule, but between two different molecules. Okay, and so just one other recall back to our Vesper theory. So water has two atoms and two unshared pairs, so 2, 2, that would equal bent on our handout. Okay, and I drew it on purpose in this structure because water molecules look something like this, where the H's are not straight on either side, they're pushed down to the bottom, but we don't see the electron pairs, and that's because electrons are so small that we can't see them. So instead, what happens is the hydrogens are pushed down, and we know that they're pushed down because of where the unshared pairs are left over on the oxygen. And so that's what creates that bent shape for us. And these are cool because they're magnetic. So if I tried, you always have the positive with the negative, right? Opposites. If I try to do two waters together, they repulse. If I try to do two oxygens, they repulse. I have to have an oxygen with a hydrogen in order for it to bond up. Okay, so hopefully this was a helpful review and or just get it down for the first time. I'm sure there's other videos out on YouTube to help you as well, but this is a big part to get the hang of for chemistry for this test.